Okay, we're very happy to have Dino Rossegger here to speak on the Borel complexity of first order theories. Go ahead, Dino.
Thank you, Arthur, and thank you to Roman for the invitation to speak in the seminar. It's a pleasure. So today I'm going to talk about a project which is joined with Uri Andrews, David Gonzalez, Steffen Lemp, and Hong Yu Zhu. And I think Steffen has given some talks about this project, and the project has since evolved quite a bit. At first, I think it was a project which actually fit very well into the topic of this seminar, but by now it kind of like evolved into something a little bit more general. But so the project has like, I guess its roots in, I guess like Peano arithmetic. Namely, it started with the following question I asked a couple of years ago on Math Overflow. Namely, how complicated is the set of countable models of true arithmetic? Where true arithmetic is just the first order theory of the natural numbers, the discrete summing of the natural numbers. And well, true arithmetic is, I don't know, maybe the most famous, if not one of the most famous theories in logic or in mathematics. And I don't know, I always think that true arithmetic is very complicated. Like, I mean, there's many theorems that somehow testify in some way to the nature that like true arithmetic is like a complicated theory. So we have like things like, I don't know, Tarski's undefinability of truth, Tenenbaum's theorem, Solovay, who characterized the degrees of the non-standard models. That's more like a computability theoretic sign that it's complicated. He showed that the non-standard models of true arithmetic are exactly the models who complete the Scott set that computes all arithmetical sets. I mean, you don't have to know what this means exactly. Also, I mean, I just to advertise my own work a bit, like Antonio Montalban and I recently showed that non-standard models of true arithmetic are structurally quite complicated. They cannot have finite Scott rank. So that's also a testament that somehow true arithmetic is like a complicated theory or like a powerful theory. And in some sense, I always have the impression that like its first order properties somehow dominate and like, I don't know, spread into many other areas, where kind of like this complexity then shows up. Like as for instance, Solovay's characterization or Scott analysis. And well, on Math Overflow, I asked this question, like how complicated is the set of countable models of true arithmetic? How do we even grasp this complexity? Well, in order to classify or like to stratify the complexity of a set of countable objects, it's very useful to use descriptive set theory and to use Borel complexity. So this is where this all started. I mean, I think I asked the question in 2020, didn't think about it for a long time, and then Steffen, Uri, and I started working on it, and then David and Hong Yu came on board. Yeah. So before I talk more about this question, like our results that kind of lead to this classification of Borel complexity of like first order theories, let me give you like a mild introduction to remind you of all of the notions. So first, okay, Borel complexity. I'm pretty sure most of you have seen this. So the Borel hierarchy, like if I'm given a Polish space, then the Borel hierarchy is a way to kind of stratify sets in this Polish space, to define a complexity for subsets of this Polish space. Namely, for a countable ordinal alpha and X, a subset here, I already wrote mod tau, but like any Polish space, think about 2 to the omega or so Cantor space, Baire space, whatever. We say X is sigma 1 if X is open, X is pi 1 if X is closed, and X is sigma alpha if X is the union of a countable union of sets that are of complexity pi less than alpha. So like pi beta sets for beta less than alpha. And X is pi alpha if X is an intersection of sigma less than alpha sets. So I guess it's a very common definition, and like basically like this Borel hierarchy basically captures all the Borel sets. Like all the Borel sets will show up at some level in this hierarchy. where the Borel set is just, you know, like if you take the sigma algebra over the open set. Okay, so now I want to talk about like this space here that I have here, mod tau. So what is mod tau? Well, if I have a countable relational vocabulary, say tau, then the set of countable tau structures that have universe all natural numbers, they admit a canonical Polish topology. How does this Polish topology look? Well, we can just fix an enumeration of all the atomic tau formulas, and then consider the so-called atomic diagram of the structure A, where the atomic diagram is basically a string in Cantor space, so it's infinite string of 0 and 1s, where the ith bit of the string is 1 if the ith formula in this enumeration, where now I replace the open open variables by the numbers by their indices, holds in the structure A, and it's 0 otherwise. So basically we get a map from that. We get a map that maps the structure A to its atomic diagram, and this is actually a homeomorphism from the space of models in the vocabulary tau, space of countable models, to Cantor space. So we get like a very, very natural Polish topology in mod tau, and we can talk about Borel subsets, or like any subset of this Polish topology, in particular about like, I don't know, pi alpha, sigma alpha subsets in the Borel hierarchy. If you're not working that much with descriptive set theory, that might all be like a little bit abstract for you. I like to think about it more in the following sense, namely in the using the connection with infinitary logic. So the logic L omega 1 omega is similar to finitary first order logic, except that it allows countable conjunctions and disjunctions. So you just have like quantifiers as usual, but you also have like countable disjunctions and conjunctions, where the truth value is defined as you would think, like a countable disjunction is true if like one of the disjunctions is true. A countable conjunction is true if all of the conjunctions are true. Just a disclaimer, in this talk, I will often write first order logic. And if I write first order logic, I always mean like finitary first order logic. I mean, strictly speaking, this L omega 1 omega is still a first order logic. So just not to be confused. And so if I take a formula phi in L omega 1 omega and alpha countable, I say that phi is in sigma 0 if it's finite and quantifier free. It's sigma alpha if it's a countable disjunction of existentially quantified pi less than alpha formulas, and it's pi alpha if it's a conjunction of universally quantified sigma alpha formulas. One can show that every L omega 1 omega formula is equivalent to a formula in this hierarchy. And so there's like this theorem, this old theorem by Lopez Escobar, which basically connects the L omega 1 omega definable sets as subsets of the space of models with the Borel subsets of the space of models. Namely, for any isomorphism invariant subset of the Borel of the space of models is Borel if and only if it is L omega 1 omega definable. And then a few years later, Watt actually gave a different proof, and if you track down this proof, he actually proves that an isomorphism invariant subset X is pi alpha in the Borel hierarchy if and only if it is definable by an infinitary pi alpha formula. So you have like this nice correspondence between Borel sets and infinitary logic. So if I talk about a Borel pi alpha set, and I will only talk about sets that are isomorphism invariant in this talk, then you can just think about definability by infinitary formulas if you want. So this talk is about first order theory, so finitary first order theory. So how do they fit in to all of this stuff about Borel complexity? We have just seen that the Borel hierarchy corresponds to the definable sets by infinitary logic. And it's actually very easy to see that like infinitary logic is like much stronger than finitary first order logic. I mean, here's like a very silly example that you might have encountered, like if you taught any first order logic course, like the class of torsion groups. So like groups where every element after some iteration of like multiplying it by itself returns back to the identity. And in infinitary logic, I can write down an infinitary conjunction with that is for all quantified, which basically is only satisfied if the group is torsion free, right? I just say, well, okay, for every x is either the identity, or x times x is the identity, or x times x times x, and so on. But I mean, it's a simple exercise to show that using compactness, that the class of torsion groups is not first order axiomatizable. So L omega 1 omega is strictly stronger than first order logic in general. I can axiomatize way more things in this logic. However, contrary to this, there's this old theorem by Kiesler from 1965 that says if a finitary first order formula phi is equivalent to an infinitary pi n formula, then there's already a finitary formula having n quantifier alternations and starting with a universal quantifier theta, such that phi is equivalent to theta. So in this talk, when I write for all n, I mean just n quantifier alternations and starting with a universal quantifier. So you can understand this result that, okay, well, infinitary logic is more expressive than first order logic, but it's not more efficient than first order logic. As soon as you have something that's definable by a first order formula, then it cannot be easier to define using infinitary logic. And Kiesler proved this theorem not only for L omega 1 omega, which I'm focusing here on in this talk, but for L infinity omega. So the difference is that in L omega 1 omega, all my disjunctions and conjunctions are countable, have to be countable, but in L infinity omega, I allow arbitrary large conjunctions and disjunctions. And recently, this has been reproven using a very different proof by Harrison, Trainer, and Kretschmer. So we have the Borel hierarchy. So we can now, and we have definability. So we can now say, okay, well, something is definable by, I don't know, a pi n formula, or for instance, if I give you any theory, in particular, if I give you the theory of true arithmetic, then I can just take the conjunction of all the formulas of this theory, and I get an infinitary formula phi. And this formula must be in pi omega. I mean, why is that? Pi omega, any formula in here is finitary pi n, or just has n quantifier alternations and is finitary. So this conjunction is a conjunction over finitary formulas. So it's going to be pi omega. So what I'm interested in, and what my question, when I posted it on Math Overflow, what I was interested in, I mean, of course, I noticed, I don't know, immediately or in 2 minutes, that this is the upper bound, right? I mean, that the set of models of J is going to be in pi omega. But what's way more interesting is can it be simpler? Is there maybe some pi n formula that axiomatizes this set? And notice that this is not contradicted by Kiesler's result, because Kiesler's result only works for single formulas, like a finitary first order formula phi. I'm interested here the theory, which is a countable set of formulas. So how do we show in general that something cannot be simpler, that it's not easier to define? Well, we use the concept of weight reducibility. So weight reducibility is it's basically reducibility by continuous functions. So if I give you a Polish space X, and I have a subset A of X, then for any point class gamma, A is gamma complete. If, well, okay, first A needs to be in the point class. So for instance, if gamma here is pi alpha, then A must be pi alpha itself. And for every B that's also in the point class, and B could live on another Polish space, B is weight reducible to A. That is, there is a continuous function from the Polish space Y to the Polish space X, Y, B lives on Y, and A lives on X, right? Such that Fy is in Fy is in A if and only if Y is in B. Sorry, that's a typo here. So that's a weight reduction. So it's just like if you think about like in computability theory, you have many one reductions, which is just like you have to have a total recursive function. It's on natural numbers. This is basically the analog of these, but for instance Cantor space or like for countable objects. So this gives rise to a hierarchy of degrees, and Wage proved, or it follows from results of Wage, that the Wage degrees of the Borel sets look basically like this. So first you have like the degree of the empty set, and you have the degree of the whole space. Then you have like all the Clopin sets, and then at each level alpha it goes like this. So you have like the sigma alpha sets that are sigma alpha complete. If you're sigma alpha, so like if you're in the class sigma alpha but you're not pi alpha, then you're immediately sigma alpha complete, and vice versa too. And then you have like the sets here, so the same holds for sigma alpha plus 1, pi alpha plus 1. If you are in both sigma alpha plus 1 and pi alpha plus 1, then you're delta alpha plus 1, and you're captured by the difference hierarchy. So D2 sigma alpha is just basically the difference of two, is like the difference of two sigma alpha sets. And then you can define this for ordinal levels, this kind of difference hierarchy. And the difference hierarchy captures the difference hierarchy on the sigma alpha set captures precisely the intersection of sigma alpha plus 1 and pi alpha plus 1. So the Wage degrees are somewhat nicely behaved. Every Borel set has either Wage degree sigma alpha plus 1, pi alpha plus 1, or one sigma alpha, pi alpha, or one of these delta or delta alpha for some countable ordinal alpha. And yeah, so they're quite nicely behaved. And like if we show that like first of all, if we, for instance, like for TA, if we show that any pi omega set is Wage reducible to the set of models of TA, then we know that it's right here, it's in pi omega and not sigma omega. Like, so then we know it is like really hard. There is no finite axiomatization in infinitary logic of this set.
Dino, there's a question in the chat that I'll read out. It's from Russell. It says, how far does that difference hierarchy go? Does it go up to omega or further?
It goes through to omega 1, so for all the countable ordinals.
Thank you.
Sorry, I have a hard time seeing the chat.
It's understood.
Seeing the chat. Okay, so please, if you related chat questions to me, that would be helpful. Okay, so and the main question then that we have is like, okay, like especially for TA, but in general, is the complexity of a theory set of models related to the quantified complexity of the axiomatizations that this theory can have. And so we've got results on this, and I'm going to start by presenting our result and proof sketches first for first order theories without bounded quantified axiomatizations, because I think we were very surprised that we could not only get this for the set of models of true arithmetic, but we could get this in general. And I'm just going to go ahead and show you the result. So this is basically our main theorem for the unbounded case. So for any complete first order theory T, we have that mod T is a pi omega complete set if and only if T has no axiomatization by first order formulas of bounded quantifier complexity. And well, when I asked this question like on math overflow, I thought, well, maybe there really needs to be like something about like the expressibility of a true arithmetic that kind of like makes this pi omega complete. And for sure, there are theories which have no bounded quantifier, which are not axiomatizable by bounded quantifiers, but have no pi omega complete set of models. But apparently, so it turns out that this is not true for complete theories. And yeah, so note that we don't need T to be in any way related to arithmetic for this to work. And well, of course, this theorem directly implies that complete theories which have no bounded quantifier axiomatizations cannot be axiomatized by pi infinitary sentences for any n. If we remove the completeness, then this is not true anymore. Namely, there is an incomplete theory T, that is not axiomatizable by sentences of bounded quantified complexity, so that the set of models of T is in sigma omega. So it's not pi omega complete. I'm gonna walk you I'm gonna sketch you, I guess, the proof of this theorem. So the one direction is very easy. So if we have like a bounded quantified axiomatization, so say S is a set of exist n formulas axiomatizing the set of models of T, then of course if I conjunct all the formulas that are in S, I get an L omega 1 omega sentence that is pi n plus 1. And hence by the Lopez-Escobar theorem, mod T is pi n plus 1, and so it cannot be pi omega complete because it's simpler. The other direction is, well, I would say it's quite difficult to prove, but we were very lucky that most of the work that is to be done in this proof has already been done. And it follows essentially from it follows directly actually from this lemma. So if T is a complete first order theory, for which we can find a collection of theories Tn, such that for every n, T is not equal to Tn, but T and the exist n fragment of T and the exist n fragment of Tn are equal. So I should say here that theories Tn also, I think, need to be complete. Then the set of models of T is pi omega complete. And indeed, for each pi omega set P, there's a continuous function that maps any P in this set P to a model of T and any P not in P to a model satisfying Tn for some in omega. And here I made like this little graphic here, how you can imagine like this, like how this theorem is proven. I mean, this lemma is proven, I guess, like quite effectively. Like, essentially, you're given P and you're given like this Borel description of P. And you can imagine P, because it's pi omega, it's just an intersection of sets Pn, which are in pi n. So like they get harder and harder, but you just take the intersection of all these sets. And like essentially the very, very rough idea is the following. Like basically you're asking, well, okay, at the first stage, you're like at the nth stage, you ask, okay, is P in Pn? Well, okay, if P is not in Pn, well, okay, then I just build a model AP such that AP is a model of Tn. And then if P is in Pn, well, okay, then I extend the model I have built so far, so that it has like the exists n theory of T. And I ask the same question again for Pn plus 1. Is P in Pn plus 1? Well, okay, if not, then I just say, okay, well, build a model of Tn plus 1. If yes, then I just basically continue my construction and build them and make T satisfy the sigma n plus the exist n plus 1 theory, and so on and so on. And like if it turns out that my P is in every of these sets Pn, so it's also in the intersection, then I will end up building a model AP of T. So that's the very, very rough idea. If I would not need this function here to be continuous, well, then I guess one can see that this is done, can be done. The hard part is actually to get this function continuous. So like P, for instance, like P cannot just ask, right? Am I in the pi omega set? Like asking a pi omega fact about P takes, like if you're computability theorist, it takes omega many jumps. It's not something that P can ask. So there's a guessing procedure involved. So P can only approximate the answer. And there's like what we call an iterated priority argument involved to basically answer these questions. And so building this AP is like actually uses quite complicated machinery. However, we were quite lucky that we basically the machinery we needed was already given to us, namely by this theorem of Solovay that Solovay used. So Solovay used like already this kind of guessing machinery of iterated priority constructions when he showed that the models of true arithmetic are precisely like the Turing degrees of the models of true arithmetic are precisely the Turing degrees of all the Scott sets which contain all the arithmetic sets. So that's again like, so this is this theorem by Solovay. I'm gonna go through it in a minute, but essentially again it comes first of all from computability theory. It basically gives you this guessing procedure that we need, and second of all it also comes from a question which is about models of arithmetic in the end, even though the theorem in the end is not. So okay, Solovay's theorem reads as follows. This version is due to Julian Knight. So let T be a complete theory. Suppose that R is an enumeration of a Scott set S that is computable from a set X with functions Tn, which are not computable in X, but they are delta n in X. So basically, I need n-1 jumps to compute these functions. However, these functions, they are uniform. These computations is uniform in n. So basically, for each, so I know the index for the function in advance. And if I feed it the n-1st jump of X, then the function is going to produce exactly what I want it to produce. And what do I want these functions to do? Well, okay, I want it to compute me an index for the exist n theory, the exist n fragment of T. And if all of this holds, then T has a model of B, and the model of B will be computable from X. And additionally, there are like things here about Scott sets, which I'm going to explain. So like B represents a Scott set S and so on. Yeah. So sorry, this theorem is like has like a lot of stuff in it. So let's just go right place. So I guess we know what it means for R to be computable from X, like one set being computable from each other. Okay, what is a Scott set? So a Scott set is a subset of 2 to the omega, so infinite binary strings, satisfying, well, it's closed under Turing reducibility. Like if Y is in the Scott set and X is computable from Y, then X is also in the Scott set. If X and Y are in the Scott set, then also the computable join of X and Y is S, so it's closed under joins, is in S. And I guess the main property that really makes it a Scott set is if X is in the Scott set and it codes an infinite binary tree Tx, then also S must contain a path through this tree T. So it's somehow closed under paths through binary trees. Like that's what's special about a Scott set. So then we have here an enumeration of a Scott set. So what is an enumeration of a Scott set? Well, okay, like if I have a countable Scott set, so I mean the set S could be uncountable, but if it's countable, then I can code it into a single set. And an enumeration of a Scott set is nothing else. So if I have a countable Scott set S, the enumeration of the Scott set is just basically a real or an infinite binary string R, such that if I look at R in columns, the columns of R are precisely the Scott set. And of course they might repeat and everything, like it doesn't have to be injective, but like it's just, so that's why it's an enumeration, right? So I might have elements of the Scott set multiple times. Okay, at last, what does it mean that the model B represents this Scott set? Well, a countable model M represents a countable Scott set S. If for every complete Bn type, so a Bn type is like a bounded quantifier types with like n quantifier alternations, gamma ux, and every element of C, gamma cx is realized in M if and only if gamma is in the Scott set, and the type is of course consistent with M. So if the type is not consistent with M, then I don't need to realize it. But if it's consistent and is in the Scott set, then I need to realize it, and vice versa. These are precisely the types that I realize. So the Scott set basically determines me which model I'm going to build. So this is kind of Solovay's result that we want to use. There's a few things, like if you're very familiar with these things, you might notice. Well, for us, here what is x is going to be the role of this p. So if I have like this pi omega set big P and I want to check if small p is in P, then this is going to be x. And this theorem says, okay, well, if x is of a certain form, if it can enumerate, if it can compute this set R and so on, then there is a model B that is computable from X, but it doesn't tell us that this is in any way like uniform. So like it's hard to see that there's actually a continuous map that maps X to this model. And well, the second step is also like we want to go from the theory T to this model and not just, well, yeah, sorry, no, we want to go from P to this model given T. Okay, what else do I need to say to Solovay? So Solovay's theorem is proved using methods for iterated priority constructions. The original proof that Solovay gave is based on these worker arguments that are usually attributed to Leo Harrington. And this version above is can be found in a paper of Julia Knight. And she actually proves it using a version of alpha system. So that's another version of iterated priority constructions that she developed with Chris Ash. Okay, so how do you prove this lemma? So we're given like this pi omega set P, and we want to reduce it to the set of models of T. So we're given a small, so how do we do that? Well, okay, first we fix a theory T, which is not axiomatizable by boundary quantifier formulas. And we fix this theories Tn such that the existential fragment of Tn matches the exists n fragment of T. And okay, like we also take for granted that we have like an enumeration R of a Scott set S containing T, Tn, and this Borel code C for this pi omega set P. So essentially, I mean, I haven't explained what a Borel code is, but like, right? I mean, the Borel sets are basically given using these intersections of unions, blah blah blah. So how can I present this? Well, like I could basically like at the base sigma 1 sets are the open sets, so I can just have codes for open sets, and then I can just have basically a tree, which tells me, okay, if I'm at an even level, I take unions. At an odd level, I take intersections, and the leaf nodes are labeled with the codes for the open sets. And then basically I follow this tree, what this tells me, and then it's gonna result exactly the set. Then basically this describes me the set P, gives me a description of the set P. And then I think this description is countable. So it's like a tangible object. So yeah, we are having this Borel code C and this pi omega set P, where P is this intersection of this Pn, where all the Pn's are sigma n. So how do we prove the lemma? Well, okay, we're assuming we're given some real x, and we produce indices for these functions Tn such that Tn x n minus 1s is equal to R Tn plus 1. So here just I mean like is equal to an index for Tn plus 1. If x is not in Pn(s). So the point is Pn exists n, right? So I have an existential quantifier at the front. So basically I ask, right? Okay, so have I already seen a witness for the first existential quantifier in the first S stages? If yes, then if no, then okay, then I let my Tns point to Rtn plus 1. If yes, then I let it point to RT, and so on. And this procedure is actually recursive in so basically giving this index, producing this index, is recursive in the real X plus the enumeration of the Scott set R plus the theory T, plus all the theories Tn, and unfortunately I need to take the jump over them, plus the Borel code C. So the point is like my function needs only to be continuous. It does not need to be computable. If it needs to be a computable function that maps X to the model, then I'm screwed. But I'm allowed to give it additional information as long as I don't change this information. So I'm allowed to code these things here. So this is a continuous map which maps X to basically the string, which maps X basically to these indices. And then I basically just say, okay, hey, I have these indices for these functions, and I have my real X. So hey, great. Now I just use Solovay's theorem. And if Solovay's theorem is continuous, so basically I have a way to map from X and all these indices for these functions down to my model, then this works. Then I get like this reduction. And well, yeah, we verified that Solovay's theorem is continuous. I mean, I'm not going to say too much about this. It's like somehow people who know like these iterated priority constructions, and you talk to them, they say, oh yeah, of course it's continuous. For somebody who has never seen them, then it doesn't make sense to, I guess, like try to explain why they are continuous. It's like they are very abstract machinery. But yeah, I mean, I guess when I asked Uri Andrew, so is this really continuous? Uri was like, oh yeah, of course, without even looking. So, and I mean, of course, we checked afterwards, but so yeah. So okay, once you have like this theorem, what do we get as a corollary? Well, we get that the models of T for T a completion of Peano arithmetic are pi omega complete. I mean, why is that? Well, because we have Tarski's undefinability of truth, right? You cannot define truth in arithmetic, so they are not boundedly axiomatizable. Furthermore, also PA is the models of PA are pi omega complete. I mean, PA is of course not a complete theory, so we cannot just use the theorem directly, but we can just produce in the pi outcome, we can just produce a model of true arithmetic, and we can use we can take as these Tn's, we can just take theories which exist which break sigma n induction, but look like, so this should be sigma n induction, but look like true arithmetic for the first quantifiers. So we get that. So and this was actually also like what we set out to do originally, and this was kind of like the state of the project like a few months ago, that we had like this result. We were very happy. And then we were thinking, okay, we have this stuff for true arithmetic and completions of PA. Like, in what sense is it really well, back then we actually were not aware that we don't even need PA, because, well, essentially we didn't read Knight's theorem very well, which says it works for any theory. But so we were like, okay, what is the role of induction in PA not having bounded quantifier axiomatizations? So what happens if I just consider completions of, for instance, PA minus? So remember, I mean, I guess in this seminar everybody knows PA minus is just basically PA but without induction axioms. And Roman Kossak was visiting Vienna at the time, and Steffen and I asked him, and we asked him, so okay, like if I take a completion of PA minus, can this completion be axiomatized by bounded quantifiers? And he asked Ali Nayad and Albert Wieser, and they were, I guess, quite happy about the question, because I heard that Albert is giving a talk about this in a couple of weeks here. And basically answered this question.
Dino, that will be in March. It's delayed. It will be on March 12th.
Okay. So on March 12th, tune in for Albert's talk on, on this topic. Yeah. I will just quickly like summarize the results. So in order to understand the results, we need the following definition. So originally, sequential theories were defined, I guess, by Putlak, but this definition is from a paper from Bakomov and Wieser. And they said, okay, like a theory in the language Tau is sequential if it admits a definitional extension to adjunctive set theory, AST. So that means that if I add a new binary relation symbol, the element of symbol, to Tau, then I need to be able to define the axioms for Tau, such that I can say, okay, well, the empty set exists. And if I have a set X, then also X union the single element Y exists. So I can extend the set X. And so this is a very, very, very weak set theory in essence, this AES. And in essence, I think Putlak also defined it originally like this. Sequential theories are those theories that allow for coding of finite sequences. As in, like, if you think about Gödel's proof of the incompleteness theorem, he has like this beta function, which lets him code finite sequences. And it's basically the same thing. So basically, these sequential theories allow a beta function. Allow definition of kind of like this beta function that lets you code finite sequences. So sequential theories, there are many sequential theories. So, I mean, of course, Peano arithmetics, we know through Gödel is sequential. Induction for delta zero formulas, so quantifier-free formulas plus exponentiation is sequential. I mean, set theories are sequential, such as CF, KP, Kripke-Platek. And also Jashabek showed in 2012 that PA minus is sequential. Then, okay, Pakomov and Visser showed that adjunctive set theory itself is sequential. But interestingly, for instance, like if I take from PA minus like a few axioms away, like if I look at Robinson's Q, then this is not sequential. So then there it breaks. And so Ali Nayad and Albert Visser showed that if you have a sequential theory in a finite vocabulary, then it has no axiomatization. I guess you need the, sorry, if I have a complete sequential theory in finite vocabulary, here the complete is missing, I think, then it has no axiomatization by sentences of bounded quantified complexity. And this was, I mean, to me, that was very, very surprising because I thought, well, okay, maybe, I don't know, like PA, like the induction axiom is the only thing if you look at PA, right? The axioms, the induction axioms is really like the only thing that has like a lot of quantify alternations because it exists for every formula, but like PA minus the base theory doesn't, is like, I don't know, pi 2 or something. So anyway, so they proved this theorem, which is quite cool. It's like a very nice application, I guess, of Tarski's undefinability of truth with like a lot of other stuff. And note that the finiteness condition here is essential because, like, if you take, for instance, true arithmetic, and you take its Morleization, so you just add for every formula that a relation symbol R phi, then this has a complete then this is an axiomatization by universal 2 formulas, so pi 2 formulas, because you can, if you just look at like how Tarski defines truth originally, you can just do the same, right? You can define the truth of the pi n formula R phi by looking at the truth of the formula that's further down. By looking at the truth of the inner formula. So that's essential. And using these results of Nayad and Visser, we get that if T is sequential in finite vocabulary, then the models of T is pi omega complete. So this was basically the state of this project like a couple of weeks ago, or a couple of months ago. And then David and Hongyu came in and said, well, okay, why don't you look at what happens if you have like a bounded axiomatization? And we were also able to prove something there. It's a little bit more subtle. So like if T is a theory and N is a natural number, then the following are equivalent. T has a pi n axiomatization, but no pi n minus 1 axiomatization. And the weight degree of the set of models of T is in the interval sigma n minus 1 and pi n. So we cannot pin down directly the interval. I mean, like colloquially speaking, why can we not pin down which weight degree is exactly? Because if you think about, let's say you have like uncountably many sigma n formulas that axiomatize the theory, then okay, what do you want? What can you do? You have to take the conjunction of all these formulas. But then that's not a sigma n formula, that's a pi n plus 1 formula. So that's why you have like this interval here. Yeah, this interval contains infinitely many weight degrees because you have like the difference hierarchy. And we show that like these bounds are sharp, so this cannot be improved because we give actually examples of exist n axiomatizable theories that have weight degree sigma and pi n plus 1, and also d2 sigma n, and this can also be extended to dk for any finite k. Interestingly, we don't get theories of weight degree sigma 2 and smaller, because simply there is no complete consistent first order theory T, such that the set of models of T is sigma 2. And the reason for this is that if I write down an infinitary sigma 2 sentence, then essentially it will always have a finite model. So if I take a complete theory, then, well, okay, the complete theory has a finite model, so it's the theory of this finite model. And the finite model doesn't live in my space. I mean, that's the reason. Yeah, the theorem essentially goes almost the same way. So we have like, again, like we have like this theorem that gives us this continuous reduction, this weight reduction. And it again uses Solovey's theorem. The only difference is that we don't have to use theories T and Tn. We only have like one T plus and one T minus. And the only condition is that the exists n segment of T minus is a subset of the exists n segment of T plus. Then we can produce such a reduction F for any sigma n set, such that Fx is in the set of models of T plus if X is in X, and it's in the set of models of T minus otherwise. And in particular, the set of models of T plus is sigma n hard, and the set of models of T minus is pi n hard. And the proof is, again, uses Solovey's result just with a small twist. And additionally, we have this other lemma, which is based on a compactness argument. So first of all, okay, say a level sentence set for L is, so take a language L. The level sentence set for L is either the set of exists n sentences or universal n sentences in L for some n. So I have like all these level sets. So basically just take all the sentences that are exists n or universal n. Then if lambda is a level sentence set, and T a theory that is not axiomatizable, lambda axiomatizable. So basically the lambda part of T does not imply the whole of T. Then there are complete theories T0 and T1, such that T is actually a subset of T0, T is inconsistent with T1, and the lambda theory of T0 is a subset of the lambda theory of T1. And this is proven by like some compactness shenanigans. I want to point out that here we have like this, so basically T is extendable to T0, because if you look at our finite statement, there's no mention of T needing to be complete. So this also works for incomplete theories. So what else do we get from this? Well, we also get Kiesler's result as a corollary, like for L omega 1 omega. Namely, so Kiesler proved if a finitary first order formula phi is equivalent to psi and pi n, and Kiesler proved it for L infinity omega, and I again have a typo here on the slides. It should here, because I referenced our names here, it should be here. We only have it for L omega 1 omega. Then there is a for all n formula, theta such that phi is already equivalent to theta. And as I mentioned, our proof only works for L omega 1 omega, but not for L infinity omega. And we are actually quite excited about this because, well, Kiesler used like these infinite games. So that's like, I don't know, in my mind, it's a very complicated proof. And Harrison, Trainer, and Kretschmer used forcing with elementary extensions. So both of these proofs, I mean, the game proof, without knowing it like from the bottom of my heart, it looks like something that uses a lot of determinacy. Harrison, Trainer, and Kretschmer, this elementary extension stuff is also something that's like using kind of like almost meta-mathematical. Well, our proof is, well, I mean, it's combinatorially, I think it's harder, like because the Solovey theorem is very hard to prove. But it's simpler in the sense that it doesn't use any determinacy, it doesn't use any meta-mathematics, and it's essentially effective. Like, I mean, the whole Solovey theorem proof, it came from effective considerations. And like, if you remember when I said, like, how do we produce these reductions? Okay, we have to add like something to the oracle, but it's concrete. We can say, okay, add this to the oracle, then this works. So like for computability theories, this is very satisfying. And since all of us are computability theorists, we had to say, okay, well, let's look how effective is this result, or how effective are our results. And I'm gonna keep this short because I know this is maybe not the right audience to fully appreciate like the computability theory. But so
Russell is here.
Oh, well, then maybe I should go in full detail.
No, please don't.
Well, so okay, we say that a set of natural numbers D witnesses the gamma hardness of a set Y in counter space. If for every Borel code C for a set X in gamma, there is a Turing operator phi, so that phi given this set D plus C plus P basically gives the conduction, so gives the reduction. So there's this algorithm, which as soon as I give it D, and I'm also giving it C, because to be fair, there's way too many Borel sets out there for D to handle everything on its own. And given P, we have that the algorithm with this information output something in Y if and only if P is in X for every P into 2T omega. So in some sense, it's basically kind of like precisely the thing that computes that basically that's like the continuous reduction is the weight reduction is effective somewhere, and D is like an oracle in which the weight reduction is effective. And then if phi does not depend on C, then D uniformly witnesses the gamma hardness of Y. And then similarly, okay, we can say during degree D uniformly witnesses the gamma hardness of Y if it contains a set that witnesses the gamma hardness. And as I said before, well, our main lemmas rely on Solovay results. So they should be, so these things should be inherently somewhat effective. And essentially this is, they are. And this is precisely how effective they are. So like if T is a completion of PA, and that during degree T computes a non-standard model of T, then D uniformly witnesses the pi omega hardness of the set of models of T. On the other hand, if T is a completion of PA minus, and D does not compute a non-standard model of T, then it does not witness even the sigma 2 hardness of mod T, right? I mean, clearly every pi omega hard set is also sigma 2 hard. So like basically witnessing the pi omega hardness is much harder than witnessing the sigma 2 hardness. So like if you cannot compute the non-standard model of T, then you're already too stupid to witness the sigma 2 hardness. And so this kind of like gives like this interesting dichotomy, right? So if I fix a completion of PA, then every Turing degree either it uniformly witnesses the pi omega hardness of the set of models, or it fails to witness even the sigma 2 hardness of models. So I guess like this is, I find this very interesting from, I guess, degree theory perspective. And then also like for the result for, I guess, for the finite version. So recall that X is a subset of the natural numbers. X is PA over Y if Y is computable from X. And for every Y computable infinite binary tree T, X computes a path through T. And then if T is a theory without a for all n axiomatization, and D is PA over T, or the theory T, like I can view T as a set of natural numbers, then D uniformly witnesses the sigma n hardness of the set of models of T. Yes. So then we were thinking, okay, where does this fail? Like, does this hold for like kind of yeah, like can we have like can we witness computably? Like for which theories can we actually witness? Can we witness computably that there is that the set of models is pi omega complete? And there's this old theorem of Wilmer's. So if exists one less than is the set of bounded existential formulas in the language of Peano arithmetic, and I exists one less than is the induction principle, then Wilmer's showed that if A is a model of I exists one less or equal, then A is computable if and only if A is standard. So A is the standard model of the natural number. So basically he characterized the theories which have like this Tenenbaum phenomenon, right? Like, so basically Tenenbaum theorem holds for I guess like any theory, any theory that has like I exists one less than. So if T is a complete extension, consistent extension of PA minus plus IE1, then the set of models of T is pi omega complete. But we cannot computably witness the sigma 2 hardness of models of the set of models of T. And I mean, why is that? Well, basically, because if I take a pi omega set that contains a computable element, then for this computable element, I need to compute, if I want to be computably witnessed, I need to compute the model. But the only model I can compute is the standard model, like from this computable element, because the element is computable, and then I have an algorithm that computes something from that. And the standard model is simply way too simple. Like it can never witness pi omega completeness. It cannot even witness sigma 2 hardness. So for these theories, like kind of like even already this computable witnessing thing fails. Interestingly, if you drop this I exists one less than, then Shepardson showed like already a long time ago that there are computable non-standard models of PA minus. So I guess we haven't really looked too much into this, but I think it's an interesting question to see if there's a complete T of PA minus, such that actually there's a computable witness for this pi omega hardness of the set of models of this completion. We know that it cannot happen if we add bounded induction, but can it happen if we don't have any induction? So that's my last question, I guess, for you, and thank you very much for your attention.
Okay, let's thank our speaker. Thank you very much. So, we can open it up for questions. So, feel free to unmute yourself and go ahead.
Maybe you said this earlier on, late, but what meta theory are you using for these results? Is it ZFC? Is it singular arithmetic? I'm asking, of course, because of the use of the Borel.
So that's a that's a good question. So far we haven't really looked into what kind of like meta theory you need to prove this. I guess mainly because I guess none of us really are like too inclined to do that. I have the suspicion that essentially you can prove this theorem using WKL0. Like, so my suspicion is that you don't need any kind of Borel determinacy, and that if you're very careful in like kind of coding, then you can prove this theorem using WKL0. Because my suspicion is that it's in the end it's some kind of compactness principle. But yeah, I mean that's just a suspicion. I think that like many things can go wrong there by what I just said, and I guess I'm not working a lot with these things, so I would have to really sit down and track that down, which maybe I will. I think it's a interest. It would be a cool result to show that kind of like this first order, that this statement that basically this like our theorem can be seen as another extension of like this theorem of Kiesler, right? That kind of like infinitary logic doesn't give you more efficiency, and it would be cool to show that this really just is like a compactness thing. Like if you prove it in WKL0, then you show it's just a compactness thing.
Okay, so if there are no more questions, I don't have a question, but I just want to reiterate what I said before, that Albert Visser will be talking about his and Ali and Ayat's results on March 12th. So there will be a follow-up, but also 2 weeks from now, Elliot, who's here, will talk about models of PA that are Borel. And I understand that Elliot did solve Canave's problem, the question whether there are Borel models with a full standard system. So we're certainly looking forward to that. Elliot, if you want to say a couple of words on that, maybe you could, but if not, we can wait. But it won't be next week, it will be 2 weeks from now.
Yes, that is basically what I'm talking about. And sorry, I'll send my abstract later today.
All right, so it will be posted soon. And just about Shepardson. So Shepardson did show not just that there are computable non-standard modes of PA, but PA minus, but also of open induction. So there is some induction there. But also, Jim Schwell, who's no longer here, he was listening. He has this curious result that there are non-standard models of PA. Well, neither multiplication nor addition can be computable, but the divisibility relation can be. So I wonder if this could be used for something.
Okay, let me take a note of that.
Yeah.
I don't know, but it's an
Yes.
interesting point. So that's Jim Schmerl.
Yes, and this is in the paper. We have a memorial. This is this ASL lecture, the sort of series. We had a memorial conference for Tenenbaum at the Graduate Center, and this is so there is a Richard Kay's article about Tenenbaum's theorem, and then Schmerl's result, but he has this generalized Tenenbaum property for what he calls definable reducts.
Okay, cool. I will take a look. Like it would be interesting for I guess the last question. Thank you.
Okay. So if there are no other questions, I'll stop the recording here. And again, just remind everyone that our next talk is in 2 weeks, as Roman mentioned, with Elliot, who's here, who will speak then. So thank you all.